In relation, I already discussed reflexive, symmetric and transitive relation. Next I will discuss combining relation. We can combine multiple set in the same way we can combine multiple relations. Because relation from A to B are subsets of A Cartesian product B, two relation from A to B can be combined in any way two set can be combined. So how we combine these sets? We can also combine the relation. Let's see one example. Let A equals to 1 to 3, B equals to 1 to 3, 4. The relation R1 contain 1, 1, 2, 2, 3, 3. R2 contain 1, 1, 1, 2, 1, 3, 1, 4 can be combined to obtain. Now we'll combine this relationship. First union R1 union R2. In case of union, both set elements will be present. Here both relation order pair will be present. So 1, 1, 2, 2, 3, 3, 1, 1, 2, 2, 3, 3. From this 1, 1, 1, 2, 1, 3, 1, 4. So all order pair will be present in R1 union R2. Next is R1 intersection R2. What is common in both relation? 1, 1. So R1 intersection R2 will contain just 1, 1. Next R1 minus R2. What is present in R1 but not in R2? It is 2, 2 and 3, 3. So R1 difference R2 contain 2, 2 and 3, 3. Next R2 difference R1. R2 difference R1 will be 1, 2, 1, 3, 1, 4. All order pair except 1, 1 as it is common. So we can combine relations in the same way we combine this set. Next definition 6, it's about composition. We can also do composition of relation like function. Let R be a relation from set A to set B and S be a relation from set B to set C. The composite of R and S is the relation consisting of the order pair A to C. So R is a relation from set A to B and S is a relation from B to C. Suppose it contain A, it contain B, here it B, here it C. Then AC will be order pair where A belongs to A and C belongs to C. And for there exists an element B belongs to B such that AB belongs to R and BC belongs to S. We denote the composition of R and S by this SOR. SOR means it is composition of R and S. First R then S. Let's see some example of composition that you can understand. What is the composite of relations R and S where R is the relation from 1 to 3 to 1 to 3 4. So R contain 1 1 1 4 2 3 3 1 3 4 and S is the relation from 1 to 3 4 to 0 1 2 with S equals to 1 0 2 0 3 1 3 2 4 1. Now we need to find SOR. So composition of ROS. In R 1 1 is present, in S 1 0 is present. So in SOR 1 0 will be present. 1 1 1 0. Now here 1 4, here 4 1. So 1 1, then 2 3 3 1, 2 1, 2 3 3 2. So 2 2, then 3 1 1 0, 3 0, 3 4 4 1. So 3 1. SOR will contain 1 0, 1 1, 2 1, 2 2, 3 0, 3 1. Next definition 7, it's about the power. Let R be a relation in the set A. The power R power n. N can be any number are defined recursively by R power 1 equals to R and R power n plus 1 equals to R power n OR. So you can say R square equals to ROR. RQ equals to R square OR. R square we can find by ROR then R. So composition of RR, composition of R and so on it will continue. Let's see one example based on this. Let R contain 1 1, 2 1, 3 2, 4 3. We need to find power of R power n. So R power 1 will be same as this. Now I will find R power 2. So R composition R. 1 1, then 2 1, 3 2, 4 3. Now I will find these two composition. So 1 1 1 1 1 1 will be there, 2 1 1 1, 2 1 will be there, 3 2 2 1, 3 1 will be there, 4 3 3 2 4 2 will be there. So R square will contain 1 1 2 1 3 1 4 2. Next we will find R power 3. This is our R square. We will do composition with R. So 1 1 2 1, then 3 2 4 3, that R contain. This is our R. So R square composition R. Now what RQ will be contain? 1 1 1 1, it will be 1 1, 2 1 1 1, so 2 1, then 3 1 1 1, 3 1, then 4 2 2 1, it will be 4 1. So 1 1 2 1 3 1 and 4 1, all are end with 1. Next we will find R power 4. This is our R power 3, that we will do composition with R. R contain 1 1, then 2 1, 3 1 and 4 3. Now composition of both R power 4, that will be 1 1 1 1, it will be 1 1, 2 1 1 1, it will be 2 1, 3 1 1 1, 3 1, 4 1 1 1, it will be 4 1. So after this, if we will find R5, R6, R7, all will be same as R3. Even R5, R6, R7, all will be same. So after this, all are equivalent to R power 3. R power n equals to R power 3 for n equals to 4, 5, 6, 7, like this. Next, theorem 1. The relation R on a set A is transitive if and only if R power n is subset of R, for n is some positive natural number like 1, 2, 3. So if R power n is subset of R, then we can say R is transitive. Now just check in this example. Here R power 2. R power 2 contain 1 1, 2 1, 3 1, 4 2. 1 1 is present, 2 1 is present, but 3 1 and 4 2 are not present. So this is not transitive. This relation is not transitive. Even R power 3, it contains 1 1, it present, 2 1 is present, 3 1, 4 1 are not present. If R power n is subset of R, then we can say a relation is transitive. I already discussed transitive in previous lecture. If AB belongs to relation, BC belongs to relation, then AC must belongs to relation. That's about transitive. With this, I am finishing this chapter. Here I discussed relation, types of relation like reflexive, symmetric, transitive, combining relation, composition of relation, and power of relation. In next lecture, I will discuss NR relation. If this lecture is helpful for you, please like, share, and subscribe. Thank you.